So thank you for the organisers for the very kind invitation. So as Pierre said, this is the first of 2 lectures concerning recent developments in non-commutative Iwasawa theory. So I've sort of allowed myself the freedom to be a little bit more expansive than Mahesh may be forced to be this afternoon, and I'll tell you something about the context of the results and describe the setup. Right, so the general setup starts with the famous Tamagawa number conjecture of Bloch and Kato. So this is Tamagawa number conjecture for M and K, let's say. M over K. This is Bloch and Kato. And given a motive, one can define its L function. One can take the leading term of this L function. You get a real number, a non-zero real number. This is the leading term in the Taylor expansion at S equals 0 of the L function. And Bloch and Kato used periodic Hodge theory to define local and global groups of points on a motive, to define a measure, a Tamagawa measure, and to use the Tamagawa measure to refine the conjectures of Bailinson and Deligne to give really a formula, a fairly explicit formula for this value to within a sign. So if you like, if I mod out by a sign, you'd really get a formula here in terms of, let's say, Tamagawa measures constructed or defined using periodic Hodge theory. So this is the seminal conjecture, which is the start of the story. In some cases, the motive may come equipped with additional endomorphisms. You may have a motive that has actions of Hecke algebra or a CM field or a group ring over some finite Galois extension because your motive has been base changed. And in those cases, actually, it turns out that it's very advantageous when formulating or defining the L function and when formulating some kind of leading term conjecture to remember that there are additional symmetries. It gives you more information. And this was the motivation for, let's say, the equivariant version of this Tamagawa number conjecture. Again, in the same context. So Fontaine and Perrin-Riou reformulated the Bloch-Kato conjecture, and they already introduced some degree of commutative equivariance in this formalism. Kato did the same. And then to establish the general form, myself and Matthias Flack sort of finished the story. And in this setup then, our M comes equipped with the action of an algebra A, which is finite dimensional and semi-simple over Q. And the L function for M, remembering the action of A, has a leading term, can be defined using reduced norms of the action of the, if you like, the A equivariant action of Frobenius. And this is no longer a non-zero real number, but rather an element of the unit group of the algebra tensed with the real numbers. And so the question was, how do you generalize this general formulation? And the answer, the most satisfactory answer, involved some algebraic K theory. And I'll just sketch that now. So the basic idea is that you assume that sitting inside your periodic realization of M is a full Galois stable lattice T, which also admits the action of an order sitting inside A. So A is a finite dimensional semi-simple Q algebra. So A sits inside A. This is finitely generated over Z. And it's full. In other words, it's an order sitting inside this algebra. And AP is its periodic completion. T is TP, but I'll suppress the P. I'm sort of fixing P. So there's a full Galois stable lattice. And the assumption is that we are in a situation where T is actually projective as a module over this order. It's stable under the order, which is an additional condition, and it should also be projective. So if you make that assumption, it turns out that speaking very quickly, convexly supported cohomology of T. If you use the notion of virtual object, which is a non-commutative determinant introduced by Deligne, the set of data that comes from compactly supported cohomology of T, when you vary P, actually, or maybe I'll carry the P for the moment, actually, but then I'll drop it soon, gives enough data to not so much give a formula for this. Remember, Bloch and Carter couldn't give a formula for this. They couldn't see the sign. So there's some degree of ambiguity in the general equivariant situation. And that degree of ambiguity is best measured by interpreting this element. In fact, it's not so much in the algebra. It's in the center of the algebra. So the center of the algebra is, of course, the target of the reduced norm map. And reduced norms are involved with algebraic K-theory. And if you introduce a little bit of algebraic K-theory, of which more later, you can specify this inside a relative algebraic K group. So this was using Deligne's notions of virtual objects. We regard this effectively as an element of a relative algebraic K group. So using relative algebraic K theory. And you'll see more of that later. I'm just and virtual objects. If your algebra Roman A is Q and your order curly A is Z, this is just the determinant of compact support cohomology. L, M, comma, Q, comma, 0 is just L, M, comma, 0. And this would recover the Bloch-Carter conjecture in the formulation of Fontaine and Perrin-Riou. So it was an attempt really to take advantage of motives that had additional groups of endomorphisms. Now, I'm going to indicate in a moment the advantage of remembering such groups of symmetries. But for the moment, let me just have on the board some general pictures. It starts with the Tamagawa number conjecture. There's an equivariant version thereof, which is the same formalism with a little bit of algebraic K-theory. Then, more latterly, there's been another version, which is called the non-commutative Tamagawa number conjecture. And that was by Fukaya and Kato. And again, we're in the same context. And what we have here, these algebras were finite dimensional. And Fukaya and Kato asked themselves what would happen to this formalism of relative algebraic K-theory if you removed the hypothesis that your algebra was finite dimensional. So, for example, if you had a Galois extension, K over K, which was profinite, each of these extensions was finite and Galois, then starting from your M, defined over K, you could pick up a motive which had an action of a finite dimensional semi-simple algebra, namely the group ring over this finite Galois group. And you could then look at the equivariant Tamagawa number conjecture for M base changed with respect to the action of the algebra. And you could ask, is there a more conceptual interpretation of the inverse limit of these conjectures? That's effectively what Fukaya and Kato asked. And to answer that conceptually, what they did was they developed a theory of relative algebraic K-theory together with appropriate generalizations of some important exact sequences for algebras which were really much, much more general than Iwasawa algebras of such profinite groups. So the interpretation of this inverse limit conjecture uses a K-theory of adic algebras. Algebras which are complete and indeed obtained as a profinite completion with respect to two-sided ideals which have finite quotient. So There are lots of conjectures like this in the literature. The advantage of each one of them, basically each one equivariant one, is the following, that in the literature there are many, many very explicit conjectures which are refinements of well-known conjectures, and this is a universal framework which recovers all of them and gives lots more things besides. So I'll just give some indication. So these are really applications. What do you get out of this general conjectural framework of an equivariant refinement of Bloch-Kato, or if you like, an equivariant refinement in the limit? What does it give you that the original Bloch-Kato conjecture wouldn't give you? So these are really applications via the ETNC, the equivariant refinement. So in the literature, as I said, there are lots of conjectures. For example, there are refined BSD conjectures that have been formulated by Gross, has a refined version for CM elliptic curves. Maser and Tate have a refined version of the BSD conjecture, which is the elliptic curves defined over Q and base change through an abelian extension of Q. Bertolini and Darmon have refined versions of BSD under certain conditions, etc. And upon appropriate specialization, all of these conjectures recovered by this general framework. You have in the literature refined versions of Stark's conjecture. Stark's conjecture is concerning the leading terms of art in L functions and their properties. So here there are 9 or 10 refined Stark conjectures, most notably again by Gross, Tate, Rubin, all different conjectures. I've forgotten, Chinberg has one, as do other people. And again, this general framework recovers each of these upon appropriate specialization. It recovers all of the classical theory of Galois module theory. So this is a situation where we have one of these base-changed motives, and the arithmetic of the motive will give us some natural objects endowed with actions of this finite Galois group, and you can ask what kind of module is it over the finite Galois group, and there have been theorems and conjectures in this context of Chinberg, Pappas, of Martin Taylor, and also latterly there have been papers of Rubin and Maser concerning the structure of Selma groups. And they're all, again, they all come out of this general picture. If you specialize and make this rather inexplicit formalism more explicit, you recover in each and every case at least what these people studied, in fact, often more besides. Other formulations that are relevant. So Lichtenbaum's theory of varietal cohomology. So there's a recent work also of Geisser, generalizing Lichtenbaum's approach. They give leading term conjectures which don't use p-adic cohomology but use a global cohomology theory, either varietal cohomology for Lichtenbaum or arithmetic cohomology for Geisser, and they fit into precisely this context. The work of Jan Nekevash on Selma complexes. Is again precisely in this equivariant setting. Selma complexes are precisely the construction that one would need to formulate main conjectures with additional groups of endomorphisms acting. It's related to lots of things in the literature. Of course, what that means is that since very few of these conjectures are fully proved, not much of these conjectures will be fully proved either. But fortunately, recently, there have been some quite major developments concerning these conjectures, so conjectures with equivariance under a certain hypothesis. And I'm going to explain the hypothesis now. This is the hypothesis that allows us to develop and study an appropriate Iwasawa theory. So the idea is to develop an Iwasawa theory appropriate to the proof of these refinements of the Bloch-Carter conjecture. That's the motivation of, if you like, non-commutative Iwasawa theory, to develop an Iwasawa theory appropriate to this setting. Non-commutative Iwasawa theory. To the ideas. What's the motivation? Well, there are two of them. The first one, at least I'm aware of, is, as I say, to formulate a main conjecture which will address the additional refinements that are built into these equivariant conjectures. So this is an Iwasawa theory relevant for, let's say, the equivariant Bloch-Carter conjecture. A second subsidiary motivation may well be, if you recall how classically one uses Iwasawa theory to prove results about algebraic K groups using cyclotomic elements, which are elements of the multiplicative group, what you do is you use Chern class maps to interpret the algebraic K groups as Étale cohomology, pass up an Iwasawa tower, and then at the top of the Iwasawa tower, use the twisting operation, twist by the cyclotomic character, to relate different Étale cohomology groups. So if you allow your Iwasawa tower to be bigger, you could use more general twisting, twisting by continuous Galois representations rather than just the cyclotomic character. Maybe you could use a twisting operation here to relate Tamagawa number conjectures or even equivariant Tamagawa number conjectures for different m. So if you have a given Galois representation, if you can define a main conjecture with respect to its field of definition, which will be a big Galois extension of Q, let's say, perhaps you could develop an appropriate twisting theory to relate the main conjecture for the motive that comes from your given representation to, for example, the main conjecture that comes just from Q, ZP1, the units. And to some extent, such theories have been developed, but only to a very limited extent at the moment. I'm going to tell you in the first hour then a little bit about what an Iwasawa theory relevant for conjectures like this looks like, and then how, in fact, rather surprisingly, it's related to classical Iwasawa theory in a rather explicit way. Okay, so what's the setup? This is the setup for such an Iwasawa theory. So it's the situation of a base change. But here, only certain kinds of base changes. This is a Galois extension of a number field small k. This is a distinguished quotient, gamma, which is topologically isomorphic to Zp. So typically, that might be the Zp extension of k. This is the closed normal subgroup H that's cut out by this k infinity. The restrictions are that G should be a compact periodic Lie group, because it makes the Iwasawa theory or the Iwasawa algebra rather well behaved. In particular, what one knows is that under this hypothesis, the Iwasawa algebra is Noetherian. This is the usual Iwasawa algebra. It may be non-commutative, but it's still an Iwasawa algebra. You just quotient by all open normal subgroups. Take the inverse limit. This is Noetherian. It's a consequence of this assumption. So it also implies that there exists a total quotient ring. If you just formally, or if you invert all non-zero divisors, you get a quotient ring. But under this general hypothesis that G is a compact periodic Lie group, this total quotient ring is actually pretty unwieldy. In general, it's rather unwieldy. So for instance, if you were formulating main conjectures, and so certain modules were assumed to be torsion modules, one condition that you would always want to assume is that if you had a torsion module with respect to some big group, and you descended, let's say via some subgroup of H, then you would still want in the descended modules, you would still want to know that they were torsion modules over the descended Iwasawa algebra. And there's no descent mechanism for the total quotient ring of an Iwasawa algebra. Something which is a non-zero divisor in a big extension may not be a non-zero divisor after you descend. Another problem is that we are going to try to define periodic L functions by means of interpolation, and at least at certain kinds of characters, and this algebra is just too big to have any meaningful notion of interpolation applied to it. So the insight of the people who first set up such an Iwasawa theory in this context was that, in fact, under certain hypotheses, there is a subalgebra of Q, a partial localization of lambda G, which is better behaved. That's why we assume there's a distinguished gamma isomorphic to ZP. And if you do make that assumption, you can sort of partially localize the Iwasawa algebra and then generate a meaningful Iwasawa theory. So the additional assumption looks rather strange. So let's set, so now my T is TP, P is fixed, and let me set TK to be T, tensor it up with the full Iwasawa algebra of this big group. G is the Galois group of K over K. Okay, so with this notation, the hypothesis, the additional assumption, if you will, is that if you look at the Selma module, in the sense of Bloch-Kato of TK, so it's a little bit complicated. If you mod out by its p-torsion submodule, so this is a G module, it's a lambda G module, G acts continuously. This should be finitely generated over the subalgebra lambda H. What kind of a hypothesis is that, and why is it made? So if you look at the case that G equals gamma, which is just the silly case, and not silly, of course, but the classical case that H is trivial. So your G is gamma, you just got the 6th atomic ZP extension. What this hypothesis says is that it's finitely generated over, this is then ZP. So really, it just means that the mu invariant of the Selma module of TK mod p torsion is 0. So it's a weakening of the mu equals 0 hypothesis. If slightly more generally, your G has rank 1, which means that it's gamma with just a little finite group here, then if you take any finitely generated torsion lambda G module, it will satisfy this condition. So if your G has rank 1, this is in fact no restriction. If you happen to know this is torsion, it's no additional restriction. It means the same as being torsion. But when your G gets big, this is a rather poorly understood restriction.
By two meters, we really mean not P power torsion. We literally mean just things annihilated by P only knows.
Oh no, P infinity if you like. P power torsion, yeah. Is that your question?
Yeah.
Well, that's my answer anyway. So, yes.
When you have the Selma group over this huge field K,
Yeah.
what's the Selma condition of P?
So it varies. I'm being sort of quite vague here, because it will vary in different situations.
And will this hypothesis be sensitive to how it goes?
Yes, and sometimes it will be true and sometimes not. This is sort of a paradigm within which you can formulate main conjectures, which speak about these other equivariant conjectures. It's not always satisfied, but there are people who hope that it's satisfied quite generally.
I'm sorry to
Yes, of course.
After you mod it up by P power torsion,
Yeah.
then you have something that's free over ZP. Or I mean, torsion free, then how can it have mu?
So I'm not understanding.
Like, shouldn't it be that when G finitely generated over ZP? Like,
Yes, that's the trivial group. If that's the trivial group,
but I mean, like, I'm just
that's the
thinking like
ECP.
basic structure theory of
Yes.
lambda modules in my head here. Once you've killed off all the p power torsion, either it was a torsion lambda module to begin with, or it wasn't. And you're saying it was a torsion lambda module to begin with should be the condition, but should be no mu left over after you've killed off the p power torsion.
No, I mean, there are examples where when you've killed off the p torsion,
I'm saying when G equals gamma.
when G equals gamma,
That's-
so when G equals gamma, this condition is, for a torsion module, automatically satisfied.
Right.
Right.
But
This
for
is what I'm
a
saying.
torsion module, yeah.
Well, I was saying that more generally, it just means it's torsion. Okay, maybe we clarify this afterwards.
Okay.
Let me give the lecture. Okay, so let me give some examples. Let's take an elliptic curve. Over K. And this hypothesis in this particular case, if you choose your T appropriately, the p-adic module, tape module of the elliptic curve, if you take so this is now Selma in the classical sense, you take its Pontryagin dual, you mod out by p torsion, and this should be finitely generated over lambda h. That's the hypothesis. That's the kind of hypothesis. That's not always going to be true. If you take, let's say, K now totally real, if you choose your T appropriately, then the hypothesis will be about a Galois group. And if xk is the Galois group of the maximal, let's say, maximal pro-p extension of K, which is unramified outside P, the hypothesis is that this guy, mod its p torsion, should be finitely generated over lambda h. So in this context for totally real fields, the famous conjecture of Iwasawa, of course, is that xk is finitely generated over zp. So if G has rank 1, H is finite, this is finitely generated over zp itself. This is a weakening of the Iwasawa conjecture. Alas, there's not really that much evidence for it, but for the purposes of the talk and for the purposes of generating Iwasawa theory, this is just as I say, a condition which, if satisfied, allows you to develop an Iwasawa theory. There are some people who conjecture, sorry, I should say that this setup is the setup in the paper of Coates, Fukaya, Kato, Sujata, and Venyakov. And in that paper, there's a conjecture, or they inch towards a conjecture saying that for certain kinds of K, they expect this to be true for elliptic curves. But I'm not sure that all of the authors believe the conjecture. But you can formulate a theory which will then apply in some cases. In the context of totally real fields, it's a conjecture which weakens the Iwasawa conjecture and so should be true. Right, now how do you put this hypothesis into some algebraic framework? You localize your Iwasawa algebra at the appropriate OR set. So that means you take the elements of the Iwasawa algebra which satisfy the condition that if you divide the Iwasawa algebra by the ideal on F, it should be finitely generated over lambda h. So that turns out to be an OR set. It's multiplicatively closed. It has no zero divisors. And so you can localize the Iwasawa algebra at that set. So if you do, you get something that sits between lambda g and its total quotient ring. In fact, if you look in their paper, this business about dividing by p torsion means, in fact, it's also appropriate to kill p. And this, again, sits between lambda g and its total quotient ring. So the idea really is to formulate an Iwasawa theory with respect to the localization of lambda g at either this or with respect to either s or, if you like, s star. So you have to assume that certain complexes or modules are torsion. Satisfying this hypothesis here just means that if you extended scalars up to s star, you would die. So the summer module dies if you extend scalars to s star. That's what the definition of S and S star guarantees. So a basic fact is that if you look at this complex, depending on your context, I'm only really going to deal with two contexts throughout the talk. It's either will be an elliptic curve or the ideal class groups of a totally real field. So for the ideal class groups, I realized I should have made one additional restriction here, that K doesn't ramify too much. Unramified outside a finite set S. Okay, so then if you look at the cohomology, the compactly supported cohomology, when you've thrown away S and P of Tk, if you're dealing with the elliptic curve, it's an appropriate Selmer complex, which I'll just write like that, in the sense of Nekovac. So a basic fact of the theory is that this is a perfect complex, which means it's isomorphic to a bounded complex of finitely generated projective lambda g modules. So that means it has invariance in algebraic K-theory. That's a well-known fact. What's not a well-known fact, but is the hypothesis, is that this guy dies when you extend scalars to S star. So the assumption translates into the assertion that C dot tensor lambda g S star is acyclic. It dies. Acyclic just means it's quasi-isomorphic to the zero complex. All of its cohomology groups die when you extend scalars up to S star. So if you have a perfect complex with this acyclicity condition, general formalism gives you a refined Euler characteristic in quite a fine version of algebraic K-theory. So this acyclicity if you like, gives you a refined Euler characteristic. Yeah.
You wrote tensor L, but because this is flat right now.
It is. I could have not done that. But formally I should. But you're right. There's a refined Euler characteristic, let me call it chi ref of C dot. And it lives in what's known as a relative algebraic K group. Now, the relative algebraic K group is best understood explicitly in terms of generators and relations. For the moment, let me just say briefly that if, for example, my G is equal to gamma, so that's the classical Iwasawa algebra, that's its total quotient ring. This algebraic K group in that case just identifies canonically with the multiplicative group of invertible lambda ideals in the total quotient ring of lambda. Right, so the refined Euler characteristic would be the characteristic ideal of a torsion module, for example, as an element of that multiplicative group. So relative algebraic K theory actually gives you a boundary map from a Whitehead group, call that delta. So this is just the infinite, or the abelianized infinite general linear group of this algebra. And the idea would be in the main conjecture, since this is the analog of the characteristic ideal of some torsion module, the idea would be to pick a periodic L function in the Whitehead group. Now, the kernel of delta is, in fact, the image of the natural map from K1 of lambda g. So the kernel of delta is, in the classical sense, if g is gamma, this is just the units of lambda. So picking a pre-image of a characteristic ideal under this is the same as picking a generator. So if you could define a periodic L function sensibly in this group, saying that its image under delta would equal the refined Euler characteristic, would be saying classically that this periodic L function generates the characteristic ideal of your chosen module. So that's the idea. Now, of course, what kind of element would have any right to be called a periodic L function in this kind of strange group? So that was the insight of the 5 authors, specifically that you could define such an element, or rather describe its interpolation properties with respect to evaluating, if you like, at certain kinds of representations of G. So I'm now going to say, what does it mean for something to be a periodic L function in this setting? So representation of G is an Artin representation if it looks like this. Take some finitely generated ZP algebra. You have a continuous homomorphism with the property that rho of G is finite. So it's this bit here. It's an Artin representation, so-called Artin representation. Now, if you have an Artin representation like that, let's suppose rho. So rho goes into MNO, and G surjects onto gamma. So you could map your G to rho of G cross G bar. So G bar is the image of G in gamma. And it turns out that the localization that I introduced allows you to extend this. It induces a map. If you like, let's call that phi of rho. It's a homomorphism from this Whitehead group to the total quotient ring of lambda gamma, maybe after extension of scalars, because there are some coefficients that we might be forced to look at depending on where rho lives. So the interpolation property now would be that there should exist an element of this Whitehead group such that at each Artin representation, if you looked at the image under this homomorphism, you've got a power series, and the leading term of that power series at 0 should be related to the value or leading term of classical periodic L functions for the rho twist of your representation that you started with. That was the idea. So what it looks like is the non-commutative main conjecture for k over k and t. This, as I say, is Coates, Fukaya, Kato, Sujata, and Venyukov. And it says this, that there should exist, if you like, a periodic L function in K1 lambda G A star such that both. So firstly, it should be, it should generate the characteristic ideal, if you like. So the image under the connecting homomorphism should be the refined Euler characteristic. And secondly, it should satisfy the appropriate interpolation conditions. So that's for every Artin representation. If you looked at the image of your C under this homomorphism phi of rho, so you have an element of the total quotient ring of gamma. You could take its leading term at 0, and then depending on the context you're in, there should be an explicit formula for this in terms of, let's just say, the leading term at s equals 0 of the p-adic or even complex L function of the row twist of t. So I'm not going to be precise. Mahesh will be precise about this formula in a particular case this afternoon, but that's the philosophy. There should be an element of the Whitehead group which measures the Euler characteristic of your arithmetic complex and satisfies a whole host of interpolation conditions involving the leading terms of p-adic L functions of row twists of t. Yes. I mean, for the formulate the conjecture, this is hard enough, but it would be nice to know how also it behaved under appropriate twisting by continuous representations. And if you look at the non-commutative main conjecture of Fukaya and Kato, non-commutative Tamagawa number conjecture, they hypothesize additional twisting properties that, if you twist it in the appropriate sense, you should get the p-adic L function for the twisted motive. Yes.
Is one somehow secretly in the ordinary case or something, because you end up in lambda of gamma and not?
Say again, sorry?
Is one sort of, you're not secretly in the ordinary case because you're ending up in lambda gamma?
No, certainly. When I have an elliptic curve, I'm assuming that it has good ordinary reduction at p.
Okay, so this thing in lambda gamma, this will be, if I fix that row in the rational cyclotonic twists, this will be that p-adic function of that cyclotonic.
So again, this all factors through finite extensions. If I've got my row fixes a field, and so if I take the field generated by the field of definition of row, if you like, I join it to k infinity, it all happens through a finite extension of k infinity. This will not be abelian in general.
But I mean this gamma is a ZP extension.
Correct, yeah,
So
it's this one.
It has all its chi's.
Yes.
So if I fix that row, I can kind of think about that mode of kind of up that ZP extension. And then this will be the...
Oh, sorry, yes, yes.
And if you knew all those, I mean, maybe if you sort of knew all those,
Mm-hmm.
would you kind of determine this element in the Whitehead ring, or could there be another kernel even if you knew all those p-adic
So
functions?
you might be tempted to believe this specifies it uniquely, but nobody knows that yet. I mean, there's a well-determined kernel, and you might be expected, you might reasonably expect this to be 0, but nobody knows that yet. So, for instance, in the rank 1 case, it's related to, but not equal to, a conjecture of Suslin. The uniqueness part. So some remarks. So if we write our K as a union of finite extensions, so let me just tell you how all these things are related. So we have this non-commutative main conjecture for this given extension and the given representation T of that's the lowercase c. Whoops. And we have the ETNC for the motive, for T and the finite extensions Kn over K. And we have the non-commutative Tamagawa number conjecture for K over K and T. And how are these related? They should obviously be related. So this is an implication, but you need some hypothesis for that to be true. You need some kind of semi-simplicity hypothesis. So together with the semi-simplicity hypothesis on the Galois cohomology, so in the case of number fields, that's the equivalent to Leopold's conjecture. In the case of the elliptic curve case, it would be non-degeneracy of the p-adic height pairing. But under such hypotheses, you can make a very sensible theory of descent in this non-commutative setting, and you get an implication like that, which I did with work with Ottmar Venjakob. So as I phrased it, a little bit, it's certainly unfair. If you put together all of these equivariant Tamagawa number conjectures, you effectively get close to the non-commutative Tamagawa number conjecture for Kaya and Kato. And how does that differ from this main conjecture? It differs in a really essential way. This conjecture makes an hypothesis about torsion modules. This one never has to make any hypothesis about torsion modules. So plus a torsion hypothesis, you go this way as well.
So you made the assumption that you made about stuff.
Exactly, yeah. So this one, because it comes up from a limit of things at finite level, never expects anything to be torsion, never requires anything to be torsion. It's just the torsion hypothesis is necessary to formulate a conjecture in the framework of these localized algebras. And then the point is that framework is compatible with the equivariant conjectures at finite level. So I sort of indicated as I went along, but didn't ever say, that if G equals gamma, then this formulation, in terms of algebraic K-theory, this was the multiplicative group of invertible lambda ideals inside its total quotient ring. This was the multiplicative group of the total quotient ring. This would be the periodic L function in the total quotient ring of lambda. This unwinds to a classical main conjecture. If G, let's say, abelian of rank 1, then the main conjecture, or non-commutative main conjecture, sorry, is just a classical main conjecture. It's just, let's say, the classical main conjecture. So this was the conjecture that was formulated in the 5-author paper in this general framework. You'll see a concrete example this afternoon. And then the difficulty in studying it was the complications of these big K groups. Nobody properly understood what they looked like, and so it seemed difficult. And so Kato, in his typically poetic language, at some stage asserted that he thought the proof of a main conjecture in this setting was somehow in the infinite distance. But fortunately, that's one of the very rare occasions where a prediction was slightly off. And the basic idea is very straightforward, which is that since in the rank 1 abelian situation it's a classical main conjecture, your given group, the gamma group of the big extension, has lots and lots and lots of rank 1 abelian quotients. If you assume somehow that the classical main conjecture of the appropriate kind was true for every such abelian rank 1 quotient, then it would feed you, it would give you lots and lots of periodic L functions. And the idea is somehow that this main conjecture should follow from the validity of the classical main conjecture for enough rank 1 abelian subquotients, together with an assertion that the associated periodic L functions were compatible in an appropriate way. And so that's somehow the way into this particular kind of main conjecture. So, if you like, the main result of this talk, because it somehow motivates the strategy that Mahesh will use very nicely in the second talk, looks like this. So, let's compare the Iwasawa algebra for this big, ugly group to the Iwasawa algebras that we understand well for every rank 1 abelian subquotient. So let's define a map. Delta of G from K1 of lambda G S star, and then it goes to a product, and I'm taking a product over sigma, and I take the total quotient ring of lambda sigma and its unit group, and I'm letting sigma run through so sigma is a rank 1 abelian subquotient of G. These are the functorial maps coming from K-theory. So then maybe I come here. So I'll be more precise.
I guess you're going to look at all these gamma extensions for all these rows, so you have this.
Effectively. But over finite extensions of the bottom field. Yeah. So U is open in G, and J is normal in U. This is abelian and of rank 1.
So this will be finite index.
Yes. Yeah. So the theorem would be then that the non-commutative main conjecture for this big extension and this given representation T is valid if and only if both. Well, obviously you want all of the relevant abelian main conjectures to be true. So let's say the main conjecture. So remember, all of my sigmas are U over J. So the main conjecture for Kj over Ku of T, this was the representation of the big gamma group, so you restrict it to U. This is the main conjecture. This should be valid. And 2, for all rank 1 quotients, so these need not be abelian, Q of G. If you look at the p-adic L functions that this data gives you, these main conjectures are valid, supposedly, so they each give you a p-adic L function. For the extension Kj over Ku, T restricted to U is the representation. If I let my sigma, which was U mod J, run through subquotients of this Q, I now fix a rank 1 quotient Q. So let me just say U is contained in the kernel of G to Q. Is that right? Sigma is a subquotient of Q. This vector should be in the image of this map, with G replaced by Q. So what happens is that if you have all of the main conjectures for the abelian rank 1 quotients and the p-adic L function that satisfy an appropriate compatibility relation, so in this version, what it means is that as a vector, they should belong to the image of this map delta G, where G is now replaced by an arbitrary rank 1 quotient of G. Then that's together enough to get the main conjecture in this very much more complicated setting. So some remarks about the result. The result is just abstract. It's obviously a computation in algebraic K-theory rather than a theorem in number theory. But some things it says are quite striking, which is that no matter which field K, big K over small k you started with, in fact, the main conjecture for that big extension in the sense of Coates et al. Is totally determined by the corresponding main conjectures over rank 1 extensions of the bottom field. So that means you only ever need to look at fields where K infinity, K, and this guy is finite. So somehow they totally determine the main conjecture for any compact p-adic Lie group of high rank.
So what does he say in concrete terms about p-adic L functions that you are?
So I will refer to that in a moment, but you have to understand the image of that map, and you can describe the image of that map. Somehow, by general theory, one knew that one should be able to describe the image of that map in terms of congruences. But it was difficult to spot what the congruences would be. And that's Mahesh's very nice result. It's algebraic in nature, and it describes the image of that map. In fact, slightly weaker than that, but basically it describes the image of that map in a really pretty way. And so then you could feed that information together with this theorem into saying that the non-commutative main conjecture modulo the torsion hypothesis would be valid if and only if these classical periodic L functions satisfy a whole bunch of congruences. And it turns out in the case of the totally real fields and T equals ZP1, the classical theory of Hilbert modular forms actually allows you to prove the congruences. So that's been the most recent developments.
So in this finite case, can you sort of think of it that you wanted to sort of just make like major Tate elements in the kind of classical finite group case, except that they actually kind of have an extra gamma variable?
We can talk about it afterwards. It's a little bit more difficult than that. The K-theory is a little bit more complicated.
Sorry, David, I'm
Yes.
confused. Over here, it looked as if you were taking a finite extension and then a ZP extension, whereas over on the middle board, you seem to be taking a ZP extension and then a...
So the hypothesis, the universal hypothesis, is that your field contains some ZP extension which you choose to specify. You know, like for example, this could be the cyclotomic ZP extension of K.
So they've all got, those extensions have all got to be somehow...
Yes, they've all got to have a copy. What I didn't tell you was that J somehow intersects with H, which was the kernel of here. You know, they've all got to have some ZP extension. So you can...
But that ZP extension, not...
It's related to that ZP extension because it may sort of sit up here somewhere. But it's if you specify K infinity, no, that's exactly right. I should say in the conjecture of Fukaya and Kato, where they formulate this conjectural framework for these adic algebras, that means they can formulate conjectures without any hypothesis about distinguished ZP quotients. The algebras need not even be Noetherian. It's very much more general. So 2 is an observation of Kato, really, which is that if you look into the proof of this theorem, which is just, as I say, algebraic K-theory, it turns out that it actually gives you a constructive method for proving the main conjecture. So describing the image of delta G is very difficult. But it turns out if you look into the proof a little bit more closely, it's enough to do something which is weaker, which is to describe explicitly a subgroup of the target which contains the image of delta G and has a certain nice property when you intersect it with all of the non-localized rings. You can actually do something weaker. So this was Kato's observation. By generalizing, or a slight generalization of the argument, so let's say the argument actually gives a constructive method of proving non-commutative main conjectures. Specifically, if you can prove all of the relevant rank 1 abelian classical main conjectures and verify using Hilbert modular forms, for example, in the class group case, they satisfy congruences. If you understood enough about the congruences, this would, via this result, allow you to prove the main conjecture. And this is what Mahesh has done quite generally. His description is a description of a slight weakening of this image, but it's perfectly adequate for this proof. So, in fact, the third remark was that in the rank 1 case, it suffices to consider this case. And in this case, there was work of Ritter and Weiss. In this particular case, the rank G is 1, K is totally real, and T is ZP1. So the case of ideal class groups associated with totally real fields, and they generated somehow a completely parallel theory in that special case, which one can show is equivalent to the kind of main conjecture that the Coates and his co-authors would formulate. Now, recently they proved their rank 1 main conjecture in this setting. So if you put it together with this theorem, because the first remark said it was enough to consider rank 1 extensions, what you got from Ritter and Weiss, and then just a little bit from this theorem, which is the general reduction theorem, which would say that if K is totally real, T is ZP1, an appropriate mu hypothesis is valid, then the non-commutative main conjecture for K over K and T is valid. So Mahesh has a different proof of this using techniques which are much more transportable. Mahesh gives a very nice description of this image. The proof by Ritter and Weiss of the rank 1 case is a little bit more involved, and it's a proof by induction on the order of the commutator subgroup of this rank 1 group. It's a little bit uglier. But together with the general reduction, you got this.
Is your hypothesis something you can verify by a finite check at a kind of quantum level, or is it something that's secretly living in a whole bunch?
No, it's finite level. It's a mu for a finite extension. You've got a K. You allow yourself a finite little rise, and mu for that should be 0. So I wanted to just indicate, so Mahesh's methods are more transferable than Ritter and Weiss. And one way is that they're sort of, his congruences are very pretty, and they are, in a suitable sense, continuous. So in particular, you could generalize this entire theory, not just for Iwasawa algebras, but for power series of Iwasawa algebras. You could add an additional commuting variable. And what that means is that this was just extremely well adapted to doing Iwasawa theory for varieties over finite fields. So if you use this general reduction theorem together with Mahesh's description of, let's say, the image of delta G, you can prove the following result, which nicely generalizes a result of Mark, Kissin, and Mack. So I'll just indicate that to end. So this is an application of this reduction theorem and the congruences of Cacte. Just to give you a flavor of what you can prove and why it's interesting. So let's take now X over Fp separated in the finite type. So let's look at groups which, so X is a geometric point. I fix the geometric point of this variety. I have a natural continuous map to the maximal pro-p quotient of the étale fundamental group of Fp. So this is just a ZP, a canonical ZP. And I assume I've got a group G, which is a quotient of the étale fundamental group that factors through this continuous surjection. This is the kind of G that the theorem talks about. There's the ZP quotient. So this setup gives you a corresponding pro covering. Corresponds to G. And then if you take any flat, smooth ZP sheaf on X, what you have is the following. So the first assertion is that if you take the compactly supported cohomology of X and you base change L, pull back and push forward in order to pick up an action of the Iwasawa algebra for G, this is a perfect complex. And if you extend scalars, even to S rather than S star, it dies. So this is the complex of the right kind. So this last result here is really a result of Malta-Witter. But then the point is that what you can then do is prove the relevant congruences. And so 2 says that there exists a zeta in K1 lambda GS star with, but even K1 lambda GS with 2 things. A, it generates the ideal in the appropriate sense that the main conjecture had to. And B, for all Artin representations ρ, if you look at the leading term of zeta at 0, the answer is the leading term of the zeta function of x for the sheaf L, and then twisted with the sheaf that comes from ρ. Ρ gives rise to a flat, smooth sheaf, L ρ, and if you twist the zeta function of L on x, take its leading term, and you get this is the formula. And so in the case that G is abelian, this is a theorem of Matt and Mark Kissin. I just want to say one more thing, which is 1 minute. So a nice corollary of this, for instance, what's the advantage of, why would you ever be interested in having a theorem of this flavor with a group which is more complicated than, for example, the groups that Matt and Mark looked at? And the point is that together with descent theory, as I indicated at the beginning of the lecture, main conjectures like this actually allow you to prove equivariant conjectures that were already in the literature. So there's one that was formulated by Ted Chinberg, which is called his omega 3 conjecture. And this was formulated in the late 80s. And hitherto, if your characteristic was P, as it was here, the only case in which this was known for a group of degree divisible by P was when the group had order P. And so the only situation where this was known previously was abelian and indeed even cyclic of prime order. And it's just it's almost a formal consequence of having a main conjecture of that kind. So I've already gone over, for which I apologize. Thank you.